Swayam Prabha. Digital India. Educated India.
In this lesson, we will look at the inverting amplifier, which is one of the standard amplifiers using an op amp. Now, the basis for the inverting amplifier is this particular circuit with a current input and feedback around the op amp with a resistor R. Now, this circuit can be derived using the principles of negative feedback, but in this case I am not going to do that. I have just put down the circuit. So, let us say this current is Is and this voltage is V naught. Then the analysis of this circuit is very easy. Really, there are only two nodes. Okay. So, at this node, if I write the Kirchhoff's current law equation, I will see that, let me call this node voltage Vx, Vx minus Vo divided by R, which is the current leaving this node through resistors, equals the current being injected into this node, which is minus Is. Okay. And we have the other node, which is the output of the op amp. As I have mentioned, we cannot write Kirchhoff's current law equation here. Instead, we write the virtual short equation at the op amp input, and that turns out to be just Vx equals 0, because the non-inverting terminal of the op amp is connected to ground, that has 0 volts, and the other terminal has to have the same voltage as this one. Okay. And if you solve for these two, you will easily see that V naught is Is times R. Okay. So, this is a very nice circuit which is used quite frequently also. The other standard circuit is the non-inverting op amp amplifier, which we have discussed earlier. Okay. Now, this has a current input and a voltage output, and this truly is a current controlled voltage source. Okay. So, the solution to this is V naught equals ISR, and of course, Vx equals 0. The inverting terminal of the op amp is at 0 volts. Okay. So, now as I said, it is a current controlled voltage source. What does it mean? First of all, let us evaluate the input and output resistances of this circuit. To calculate the input resistance, I have to apply a test voltage or a test current between these two terminals. I will use a test current because that result is already available to me, and in fact, if you try to use a test voltage, you will find that you will end up with a contradiction. Okay. So, you can only use a test current. So, I can apply I test and see what the voltage is between these two nodes, and I already have the solution to that. This circuit is exactly the same as that one. Okay. The direction of I test is opposite that of Is, but that is irrelevant, because whatever the value of Is, this Vx is 0. That is because of the virtual short between this point and that point, between the inputs of the op amp. Okay. So, that means that basically that voltage Vx is 0. So, the input resistance Ra is Vx by I test, which is 0. So, the input of this circuit presents a short circuit to the source, whatever source is connected. Okay. So, it is truly a current controlled source. What I mean by that is, if the input resistance is 0, even if the current source is imperfect, the circuit will behave in exactly the same way. Okay. Let us say the current source had some resistance across it. Okay. That is, it is not an ideal current source, but it is the Norton equivalent of some circuit which has Is and some Rs across it. Okay, again I am considering an ideal op amp here. This is in negative feedback, as you can verify for yourselves. Now, this Vx here is 0, which means that this Rs, no current flows through it. Okay. And if no current flows through it, I could remove it and it makes no difference to my circuit. Okay. So, all of this Is still flows through R. The equations I wrote earlier are still true. Okay. So, the solution to this, again you can calculate this for yourself systematically if you are not convinced. This V naught is still equal to Is times R. Okay. So, this Rs has no effect. Okay. This will always be the case if the input resistance of the circuit is 0. Okay. So, this is now the model for the input of the circuit. It has some input resistance Rn. Basically, that is the resistance between this terminal and ground, which is the input of this circuit. Now, you can see that the current that actually flows into the circuit is Is times Rs by Rs plus Rn, and if Rn equals 0, it is equal to Is. Okay. So, if the input resistance is 0, even if the current source is imperfect, all of the current flows into the circuit. Okay, and that is exactly what happens over here. And similarly, let me take this circuit and evaluate its output resistance. Okay. And to evaluate the output resistance, I set Is to 0. So, this becomes an open circuit. And I have this resistance R. Okay. Now, to evaluate the output resistance, I connect a test current. Now, this Vx here is 0, okay, and no current flows through the resistor because no current can flow into the input of the op amp. So, this voltage here is also 0. So, again the voltage across this is 0, which means that the output resistance, which is the resistance between these two terminals, is 0 volt by I test, which is equal to 0. So, this is a current controlled voltage source. This is truly a current controlled voltage source with 0 input resistance and 0 output resistance. Okay. Sometimes this circuit is used in a slightly modified way. So, let me again consider my circuit. We know that even if there is an Rs in parallel with Is, okay, the output voltage is Is times R. This comes from straightforward circuit analysis. Okay. Now, this combination here, you can see it is a parallel combination of a current source and a resistor. We can think of it as a Norton equivalent of something, and the Thevenin equivalent of it would be a voltage source in series with a resistance. And we also know from earlier discussions on Thevenin and Norton equivalents that this resistance is same as Rs, and this voltage source given the direction of current is minus Is Rs. Okay. So, these two are exactly equivalent. Okay. And now, the output voltage is still exactly the same, Is times R. And if I replace this minus ISRS by Vi, okay, I think of this circuit with a voltage input Vi and some resistance Rs which is connected to it. Okay. Then Vi will be minus ISRS and Is will be minus Vi by R. Substituting that in here, I will get the output voltage to be minus Vi times R by Rs. Okay. Now, this circuit is known as the inverting amplifier. I originally started from this idea of a current source with a resistance in parallel, but in general this resistance can be anything. It does not matter whether it belongs to the voltage source or whether you put it there. The total resistance being Rs, the output voltage will be minus Vi, the voltage source value, times R by Rs. Okay. So, this circuit is known as the inverting amplifier. If this is Vi, the output voltage will be minus R by Rs times Vi. Okay. And it is called inverting obviously because the gain is negative. Okay. And you can contrast this to the non-inverting amplifier. If I call these R1 and R2 and Vi and V0, V0 will be 1 plus R2 by R1 times Vi. In both cases, the gain depends on ratio of resistors. Okay. It does not really depend on the op amp. If the op amp is ideal, the gain will be exactly this much, 1 plus R2 by R1 for the non-inverting amplifier and minus R by Rs for the inverting amplifier. And if the gain of the op amp is finite, we have analyzed it for the non-inverting amplifier, you can repeat that for the inverting amplifier. The gain will be slightly different from that. And if the gain of the op amp is very large, the difference will be very small. Okay.